again. Okay, so let's say you already did the method of partial fractions and you were able to come up with these different relationships equal to each other, to uh, this being equal to this being equal to this. Everybody is equal to each other. Now the last two has a limitation though, that this will only be applicable if m is not equal to 1, because as you could see here, if it's equal to 1, this entire thing here will be 0. Okay, now let's say for example you were able to do, or you were able to derive this particular set of formulas. Now, the testing process is this, based on the formulas that were presented to you in the previous slide. So the plot of ln CB over CA, this being the y class, or ln of m minus xa over m times the quantity 1 minus xa, being the y again, or the ln of CB CAO over CBO CA, being the y, will all be paired with t, will plotted against t of the experimental data. Then if the plot is not a straight line, another rate form is guessed and tested. So this is in the case of case 1. If you're wondering why were this ln of CB over CA, or ln of m minus XA over m times the quantity 1 minus XA, or even the ln of CB CAO over CBO CA came from, it came from the equation that you have in here. Okay, so this is one equation for y. This is one representation rather for y. This is one for y, and this is one for y. Okay, all plotted against the t, meaning your slope for your line will be the CBO minus CAO quantity times K, or in the case of this one, that would be CAO times the quantity M minus 1 times K. Okay, that would be your slope. For all this representation, your line should have a y-intercept equal to 0. Okay, should have a y-intercept equal to 0. So this is what the testing of the guessed rate law is to be done. So this is how you're going to do it. Now, if it's not like that, then you have to guess another rate law appropriate for your given set of experimental data. Now, what is the consequence, or what generalization can we get out of the formulas that were equated in the previous slide? So if CBO is much larger than CAO, meaning if the initial concentration of your second species B is so large that C sub AO compares, or its value is negligible compared to CBO, CB remains approximately constant. Since CBO is very large, no matter how much of CBO reacted with CAO, it's just negligible compared to the original value of CBO. And as such, CB, the concentration of B at any particular time, is a constant. The reaction becomes a pseudo first order reaction. Or it could be that CBO is much larger than CAO, and we say that CA, the concentration of A at any particular time, changes very minimally, and as such, our reaction is pseudo first order. When we speak of pseudo class in kinetics, it's just like in our language, daw. Daw, first order siya. So kung dako-dako si B sa kay A, daw first order ang imo nga reaction with respect to A. If your CAO is very large compared to B, daw first order man siya. So it's a pseudo first order reaction, because it's just like your reaction rate is not dependent on the changes in the concentration of the other species that is so large in value. Its value, meaning, is unaffected even though a portion of it has already reacted with another species. So as such, we say that the rate law is independent of the concentration of that particular species. If that is the case, then you have a pseudo first order reaction. Daw, first order siya. Okay, another case is this. So you have one species, but it's bimolecular. In this case, it's still a second order reaction. So your rate law would look something like this. I think everybody understand why it should be K C sub A squared. And you change this C sub A. I'd like to annotate na lang in here. So if you change this C sub A to C sub AO 1 minus XA, and this is being squared and this is squared, this will be the corresponding expression that you have. Okay? Now, since here your variable is XA, there's a need for you to change the CA here, the DCA in terms of XA. So if you recall our discussion just a few minutes ago, the entire expression negative dCA dt should be changed to CAO dXA dt because your variable here on the right side is in terms of XA. If you do that, then you will come up or you will have a simple case of separation of variables again in DE. You transfer the 1 minus XA quantity raised to 2 in here, and that would be a case of power rule. And this will be your corresponding answer. Okay? And you have here the KT on the right side. This could also be like this. This one, I will write where this came from. You have here, this one came from CAO DXA dt, while this one came from negative DCA dt. So if this is negative DCA dt for this one, it should be paired with this. This should be your pairing right side. That way, your variable here, CA, will be the same as the variable that appears on your differential. This one should be paired with this. Okay? So if your pairing is negative dCA dt is equal to K C sub A squared, this will be your answer. 1 over CA minus 1 over CAO being equal to KT. If your pairing is CAO dXA dt to K CAO squared quantity 1 minus XA raised to 2, then this should be the corresponding answer that you will have. Still, the right side would be KT. Do you get it? Do you follow? I leave the mathematics to you. That way you can also do that in your spare time and do the maths on your own so that you can review your differential equations and calculus. So the pairing, you will have two pairings resulting to two sets of formulas. Okay, this to this and this to this. Okay, now we go to the next slide. That's for case 2. Oh, sorry. In this case, wait, guys. If you will have to do the plotting based on your guess that probably my experimental data is that for a case 2 bimolecular reaction, then this would be the corresponding plotting procedure that you will do. A plot of 1 over CA or a plot of XA over 1 minus XA all paired with T or plotted against T of the experimental data will be tested. Primarily because of this class. Your uh, your equation of the line would be 1 over CA for the Y here being equal to KT plus 1 over CAO. This one you will transfer in here. So your first equation of the line would be 1 over CA being equal to KT plus 1 over CAO. So this is your Y, this is your M, that's your X, and this is your B. Okay? Now, another thing is the one that was dictated a while ago is from here, from this one, you can isolate the XA. Sorry, guys, there. You can isolate the XA. I need to admit somebody. And you will have here XA over 1 minus XA being equal to, coming from here, you transfer the CAO in here, so CAOKT. So it's different than the equation of the line you have here. This one is your Y, and this entire thing is your M, and you have X for the T. You don't have a Y intercept in this case. Now, this is the one that is being explained here on the side. Okay, this is your Y. Now, there's a note here, very important note, that reactant ratios, meaning the ratio of the initial concentration of A and B, should be chosen such that it is either equal to, so they could be equal to each other, meaning your CBO could be equal to CAO, or widely different, meaning they could be either could either be equal or very different from each other, like maybe one is 10, the other is 5, or something like that. So in choosing this particular in this particular case, rather, of your second order bimolecular reaction, so they could be equal, and then they could be different from each other. Now, there's a case 3, and this one is when your stoichiometry, when we speak of the stoichiometry, your reaction, the provided reaction, does not agree with the kinetics. As you could see, you have 1 mole of A here and 2 moles of B. So in this case, case 3, if we may conclude, case 3 under unimolecular, rather bimolecular second order reaction is non-elementary. So this is non-elementary, a non-elementary reaction because your rate law does not agree with your uh, stoichiometric equation. This one, the provided chemical reaction. So reaction is first order with respect to A and first order with respect to B. Hence, a second order overall. So even though you see 2 moles of B here, your reaction is still first order with respect to B. And as such, your rate law is written in this form. Okay, I like to go back there. It's quite abrupt. So your reaction is first order with respect to A and first order with respect to B. Hence, the overall order is second order, though the stoichiometric equation does not agree with it. If the rate law is written in that manner, first order with respect to both species, so you have K C sub A, C sub B. And you have here negative dCA dt, and this is your negative R sub A. And we change the CA again to CaO 1 minus XA, and B will be changed to, or rather C sub B will be changed to CBO times the quantity 1 minus XB. As to the question, how did this one came about? This one, how did this came about? This is different than the first case wherein you have M minus XA. This one, it's M minus 2XA. The procedure is exactly the same as case 1. The only difference is that stoichiometrically, class, you have to remember that CaOXA over 1 is equal to CbOXB over 2. Because in terms of the provided stoichiometry, you have A plus 2B giving you the products. Okay, so it's not CaOXA over 1 being equal to CbOXB over 1, but it's now over 2 because of this. Okay, then it will be something like this. Anyway, I will give this to you as something that you can work out on your asynchronous time. You can practice derivation. Since you did method of partial fractions in dealing with the integral after separation of variables in your case 1, you can also use that same procedure in here. Actually, that's the only thing that you can use. You separate variables, you transfer these two in here. In here, after you have changed the C sub A, the dCA dt to CAO dXA dt, and then use the method of partial fractions. You will have this particular answer for your integral after you have evaluated it already. Okay? Now, when the stoichiometric equation or reactant ratio is used, let me just close this one. When a stoichiometric reactant ratio is used, this will be your corresponding final equation. Meaning, this one class is simply telling you that you use CaOXA over 1 is equal to CbOXb over 2. This one. You make use of the stoichiometric reactant ratio. You will come up with an answer that is simplified coming from in here. So this will be for your uh, case 3 for a second order, not bimolecular because it's a thermolecular reaction already. Okay? In this case, class, in this formula, your m must not be equal to 2 because your right side becomes 0. In here, when your m is equal to 2, this will be the simplified um, formula coming from the process integral already. This m equal to 2 tells you that your CBO over CAO is equal to 2, meaning the value of CBO is twice of CAO. So meaning your m is equal to 2. Okay? This is a special case. If m is equal to 2, you have this. If m is not equal to 2, meaning if it assumes any other value other than 2, this will be the formula that you will use for the third case. Now, you may have a question, what happens means if this is 3? Like this is A plus 3B forming the products. It's still case 3. Why? Because you have a second order, but not a bimolecular type reaction, but rather second order overall, but stoichiometry does not agree with your rate law. Your rate law is still this one. However, class, what you have in here will change. It will not be anymore m minus 2xa because we changed already the stoichiometry or the coefficient of b in your stoichiometric equation. So if it's a plus 3b, this will change. If this change, this also changes. And of course, the m's here also will correspondingly be changing depending on what m appear here. So if this is a 3, for example, if this is a 3, your m must not be equal to 3 in this case. Hindi ka nakaroon, wala ka na sa may masolve if your m is equal to 3. For this one, you can have probably m being equal to 3 or other than 3. But the equation, again, the equation will not be any more similar on the right side. Your right side will be affected by this one stays. Amo gini siya gyapon kay second order overall ikaw. Ang right side lang ang ma-change. All you have to do is process the mathematics, but your stoichiometric relationship should still be followed when we speak of the amounts of your species that react with one another. Now, that's only for the uh, second order bimolecular reaction. Now, we go to third order trimolecular. So, we also have cases in here. So, A, B, D. We don't use a C class in kinetics because C already represents concentration. So, we use the letter D for our species. Now, if it's elementary, it follows that your right side should be K, C sub A, C sub B, C sub D. And you can change the C sub A here to C sub AO, quantity 1 minus XA. The C sub B will be C sub BO, quantity 1 minus XB. Your C sub D will be C sub DO times the quantity 1 minus X sub D. Now, upon simplifying your terms, That way, what you have here on the right side are all in terms of XA. This will be the corresponding look of your right side of the equation. If it's written like this, you can use method of partial fractions again. Of course, after separation of variables in DE. So, tatlo na siya kabilog ang ma-transfer diri sa dalog. Your equation would be as complicated as this one. So it's expected that you will have three terms because you will have three partial fractions to follow. Meaning, you will have to look for the three undetermined coefficients using your method of partial fractions. Now, in here, when your third species is much larger than both CaO and CbO, following the concept of case 2 of your bimolecular second order type of reaction, do amo-amo lang sila gyapon. So since one is very large compared to the other two, the reaction becomes a second order reaction or a pseudo second order reaction because the species that is present in the largest amount does not whatsoever significantly decrease in value. So even if a portion of it already reacted, daw kung tanawon mo, daw wala lang siya gid na gamay. So hindi, ang imo rate law or ang imo rate of reaction is affected by the concentration of this particular reactant whose value in concentration is very large. So then your reaction is only second order or a pseudo second order reaction. So this is how complex it could be. But if you can do the math and if you have the limits, your calculator can process the integral because we have limits. You're given the initial concentrations anyhow. Unless the problem really requires you to derive. But if it's a problem that provides you with initial concentrations, the ones that you see here, class, so what I'm trying to say is this one are all simplified because you know in the first place the value of this, so you don't have to carry this one in the process of derivation all throughout. Same thing here on the third term. Okay? Now, so that's for case 1. In our thermolecular reaction, this is the most common type. This is the case 3 of the bimolecular, but it's now elementary in this case because you have one species here and one species here, but it's thermolecular. So it's the way it's written in terms of the rate law is K C sub A C sub B squared. Okay? Again, you change the concentrations here in terms of conversion and change the CbOXb in terms of CaOXa the way we did it with the Marshall thing of deriving the case 2 a while ago, in which I asked you, a lot of you, questions on how to go about it. So you do again separation of variables and method of partial fractions. M is still CbO over CaO, and you will come up with this formula. So you have this formula on top. This is copied from Levenspiel for M not equal to 2. If M is equal to 2, this will be your formula relating concentration of A after some time for case 2 under trimolecular or thermolecular reaction. Now we have case 3 also in here. So remember class, the case 3 for second order and third order type of reaction are the cases wherein your stoichiometry does not agree with the rate law. So it's non-elementary. So though you only see 1 mole of A reacting here with 1 mole of B, but your rate law does not agree with that. So your reaction is non-elementary. Again, you have to change the concentration here to conversion if you want to. If you do that, you change the concentration here to conversion. Same thing in here. But the way the formula looks in here, there was no changes in the concentration because I could see concentrations only. I don't see conversion. So meaning you stick to this one. Okay, you stick to the original. However, the CB squared should be changed in terms of CA. Kay, if you will allow me to speak in our language, hindi nyo mo man ni ma-process ang DE mo kung may CB kapag di nga C sub A imo variable. So your C sub B should be changed to C sub A or expressed in terms of C sub A. You can do the mathematics of that, I'm sure. So just change or you make all your variables agree prior to the process of integration, because you cannot arrive at the final formula if your variables don't agree or they're not the same. Okay, so there are conditions in here. This one is for m not equal to 1 and this is for m equal to 1.
Hello, Miss.
Yes.
May question ko bala, Miss. Di ba, Miss, ang M is CBO over CAO?
Mm-mm.
So may possibility siya, Miss, nga nangin fraction man sa or negative. Hindi na siya, di ba, pwede maging negative, Miss?
Hindi pwede. Hindi siya
Real
pwede.
numbers.
Real,
Positive real numbers.
positive lang gid siya kung magsinta real numbers pati negative dala. So
Positive
positive
real
lang
numbers.
siya. Pero pwede siya mag-fraction. Pwede siya
Okay. So kung
mag-decimal.
ano ba, Miss, anong gakatabo, Miss, kung ga-approach siya to 1, Miss, ano panawag sa iya, Miss? Or anong gakatabo sa reaction kung ga-approach ang M to 1?
Ano ang gakatabo sa
Like, oo. Kung ga-approach siya sa kung dapat bala nga undefined nga gakatabo or gahimo siya 1, for example, sa diri nga point.
Meaning your reaction as written as it is does not allow that the initial concentrations of the two species should not be equal. Duha man lang to siya, just like in second order, it says that duha lang man ang pwede nga case na matabo. It's either that they are equal or they are really different from each other. So in the case wherein your formula tells you that m should not be equal to 1, then in that case, that formula only works when the initial concentrations of the two species are not equal. Because if it's equal, then it cannot be used anymore.
Okay, Miss. So bali, Miss, kung ano, Miss, habang gapalapit sa hindi dapat bala, Miss, nga mangin equal.
Meaning, ina siya nga reaction, Marcel, hindi mo gid siya pwede ipa-process nga ang starting initial concentrations ng species mo equal. Kinahanglan lagyon mo gid. Duha man lang to mo, it's either different gid ang ilang concentration or equal sila. Kaya hindi na siya pwedeng equal sila, so dapat hindi gid sila lapitanay for your reaction to proceed. If you're asking me kung anong matabo sa reaction, hindi siya matabo kung equal siya. Kung equal ang initial concentrations ng species nga ipa-react mo, kag ang iyang stoichiometric equation governing the reaction is as provided, hindi siya matabo. Okay, wala ka sang ma-zero siya sa right side.
Sige, Miss. Thank you. Bali, the reaction mo proceed. Thank you.
Okay, so where were we? So that's the third type, the first, the second, and the third order reactions. But we also have zero order reactions. So these are reactions in which your rate of reaction is independent of concentration. So if you recall what happened here? Sorry, class. If you recall our discussion in the previous types of reaction wherein if the concentration of a particular species is so large that it does not changes over time, it's just the rate is dependent on the other two. So it's the same thing in here. It's a zero order reaction if the rate of reaction is not dependent on the concentration of the species that are present in your reaction mixture. So it could be dependent on some other things, but not the concentration. It's written also here that as a rule, reactions are zero order at higher concentration ranges. Again, going back to the previous notes that I have placed in the slides. It's just like zero order at higher concentrations because the rate is not anymore dependent on the concentration of the species, which has a very high concentration. So zero order reactions are those reactions actually whose rates are determined by other factors other than concentration. So it could be like intensity of radiation within the reaction vessel for photochemical reactions, or the availability or the amount of surface area available for solid catalyzed gas reactions. In this case, the rate is not dependent on the concentration, but rather on the total exposed surface area of the solids in the solid gas phase reaction. Now, you have to understand, I'll end with this, that in what we have discussed this afternoon from zero order to the third order type of reaction, guess, you will have to guess the appropriate rate law for the set of data that the problem provides. If you have already guessed and you have tested it and you don't produce a straight line with a y-intercept or with no y-intercept, then you have to go to the next particular rate law. So meaning ang GWA, you can have only 4 attempts. So you guess that it's zero order, you guess that it's first order, second order, or third order. Tani, supposed to be. But the problem is with the second order and the third order, you also have cases under those. So you have in total you may have 6, 7, 8 different guesses. That is if in any of your guesswork no straight line was formed versus the t, or concentration versus the t based on the expressions that you have derived. So in that case, there has to be a way of determining analytically the n and the k. Not just you will just have to think of the appropriate rate law. And then kung hindi mo, mag-guess ka naman liwas, kag mag-test ka naman liwat. Now, the next lesson will be that. So how do we determine the N and the K analytically? Analytically, class, pero it's not 100% analytical because part of the procedure is still dependent on graphical. So it's not fully 100% analytical in which you can solve for N and K. For the first three, you have to guess and test. But for this one, you really have to determine the N and the K by solving together with some graphical technique. Now, you may wonder why ti hindi mananggali may ara mananggali way nga ma-solve kami sang N kag K nga dutay lang nga graphical or dutay lang nga testing nga amon obrahon, dutay lang nga trial and error nga part amon obrahon. Nga ang maagi gid kami to sa tatlo to ka or apat to ka topic, zero, first order, second order, and third order. It's because if your reaction already tells you that it's first order, that it's second order, case 2, that it's third order, case 1, you know how the rate law is to be processed. There are reactions in which the problem already specified that it's third order and the stoichiometry, let's say, is comparable to a third order case 1 or a third order case 2. So if this particular process, the one that we have discussed this afternoon, is not discussed to you, then you will be left on your own to do the maths on your own because you do not understand how to set up the proper derivative. That way it will agree on what is written on the right side of your equation. There are only two things that could be written on the right side of your equation: the concentration or the conversion. Duha man lang na sila ang pwede mag-appear sa right side, the concentration or the conversion. And as such, the left side, which is the derivative, should also be appropriately represented by either concentration and conversion. So as to how you do the maths, you already know it based on these particular 4 topics that we have discussed. So the next ones will be just now relying on some kay diri sa methods of determining N and K, there's still a trial and error, but it's not a trial and error in which you have to guess and then plot and then test. No, it's just a guess and test. Just like you have an equation in your calculator, you place a value, let's say for example of 1 to the N, and you just check on whether the right side agrees with that. If it's not, then you change the value of N that you place in your calculator to a different value. So it's different than the first 4 that we have discussed, wherein there is a need for you to plot. But in the process, you learn to do the math. So that would be our lesson for next week. Now, for Wednesday, you won't have any quiz for now. For this week, for Wednesday, I will post in Canvas what you will do in the next for the 2 hours asynchronously. And then you will have to submit in 2 weeks time the corresponding problem set that you will process, or the corresponding derivation or formulas that I will assign to you. That's for kinetics. So our next quiz will be on the week next week na. Wala to quiz for this week. Okay? Any question for now? Okay, I will only post the portion of the slide. You may wonder why I did not post in Canvas the entire slide. I will only post the portion of the slide that we have discussed for now. That way mag-pair sila sang recording. And then the next set of slide that I'll be discussing, I will post again as we go along. Okay? Uh, the purpose is also for me to update some portion of the slide that I think needs also updating. Do you have any question? Okay. So must be clear. Do you have any question for the derivation? So if I were you now, you start working on the formulas later on after I have posted it on Canvas. That way you will be good at it in derivation and you understand where the different representations in the equations came from. Okay. Okay. Bye for now, class. I'll be hearing from you again later on in SEPA. Thank you.
Thank you, Miss.
Bye.
Thank you, Miss.